So with a given non-lifting flow going over a circular cylinder, we want to consider a infinitesimally small fluid element moving along the surface of the cylinder. Now, with that in consideration, what we want to do is calculate the angular locations over the surface where the acceleration of the fluid elements are at a local maximum and a local minimum. Now, for this case, we're going to use a radius of 1 meter for the cylinder and a free stream flow velocity of 50 meters per second for V infinity. Now, with that in mind, we want to calculate the values of the local maximum and minimum accelerations. Now, off to the right here, we have essentially an image of this non-lifting flow going over a circular cylinder. And now what we can do is we can try to find a relation between our polar coordinate, v sub theta, so essentially our velocity in the theta direction, with respect to our current system. So now what I'm essentially doing is just expanding out this radius here and then trying to make a right angle such that this will be our right angle and then this will be theta. So now in this case, in this direction here, this will be v sub theta, and then in this direction, that will be v sub r. So now with that in mind, we can make a relation such that v sub theta is equal to negative, because it's going in the opposite direction as our positive axis. So as we have negative 2v infinity and then sine of theta. So we're essentially taking our opposite side, right? So now, with that in mind, we can take the time derivative of this to essentially find the flow acceleration along the surface. So now we can say dv theta divided by dt, that's going to be equal to negative 2 v infinity cos of theta times d theta divided by dt. So now, the next step that we can do is we can use the relation between theta and a slight change across the surface of our sphere. So we can essentially denote that slight change as ds, and we can essentially say that will be equal to our radius times a slight change in our degree of theta. And then with this, we can essentially make a relation to then substitute theta into our original equation, where we have d theta is equal to ds divided by r. So now we can make that substitution. So we have dv theta divided by dt, and that's going to be equal to negative 2 v infinity cos theta times 1 over r times ds divided by dt. Now, one important thing to note, so we'll say note, just so we can highlight that, is v theta is actually ds divided by dt. And the reason for this is because let's say we had some arc. Oh, that's a line. There we go. So let's say we had some sort of arc, and then we had our radius going to our arc. So this will be with radius r. Now at this point here, we'll have some v theta, right? We'll have some sort of tangential velocity to that point along the surface. Now, across that, we'll have a small little section, even smaller than what I'm drawing now, and this will be ds, because essentially v theta is that change and position with respect to time across that surface. So we can essentially use that relation to then substitute back into our dv theta dt. So now we can write that dv theta dt is going to be equal to 4 times v infinity squared sine theta cos theta times 1 over r. So essentially what we're doing is we're taking this equation from before, and then we're subbing in for this ds dt, we're subbing in v theta, and then we had v theta up here as negative 2 v infinity sine theta. So that's how we got to this value here. So now we can make an important trig relation by saying that sine of 2 theta is equal to 2 sine theta cos theta. And then with that in mind, we can now get dv theta divided by dt is equal to 2 times v infinity squared divided by r, all times sine of 2 theta. And now this will be our flow acceleration. I'll just write flow accel along the surface. So now we need our, oh, we need our theta locations where our acceleration is max slash min, because we're looking for both. So the way we can do that is we can take the derivative now with respect to theta, because now we have the flow or the flow acceleration along the surface. So now we want to find when that flow is essentially at its maximum and its minimum. And we essentially want to optimize that with respect to theta. So what we can then do is we can say that d theta of d v naught dt is equal to 4 times v infinity squared divided by r times cosine of 2 theta. And we're going to say that's going to be equal to 0 because dv naught divided by dt is going to be constant. So now, in order for this to be true, because we know from our problem statement, we said that our velocity is going to be 50, and we said our radius is going to be 1 meter. So that means those can't be 0 in our equations. That means this cosine of 2 theta has to be 0. So pretty much that leaves us by saying, so cos of 2 theta is going to be equal to 0. So now if we were to essentially take inverse cosine and then divide by 2 just to get theta by itself, we get that theta is equal to 45 degrees, 135 degrees, 225 degrees, and on and on. So now we pretty much have our degrees theta, so we solved that part. So now we just need to figure out what our minimum and maximum accelerations will actually be. So we can write out that our a theta max, or our acceleration in our tangential direction maximum, that's going to be equal to 2 times v infinity squared divided by r, all times sine of 2 times, and now for this, we can use 45 degrees, because we know that 2 times 45 will be 90, and then sine of 90 degrees is going to be 1. So we'll essentially get our maximum, or we can write a theta max is going to be equal to 2v infinity squared divided by r. And then pretty much same thing for our minimum, where we're going to have our 2 times v infinity squared divided by r, all times sine of 2 times, and then this time we'll use 135 degrees, because then we get a theta min of negative 2v infinity squared divided by r. So now we have our maximum and our minimum accelerations tangent to our essentially cylinder with a non-lifting flow going across it.